I am Dr. K. Ragavendran from the Chemistry Department, Madanapalle Institute of Technology and Science. I did my PhD in theoretical aspects of lithium batteries at Central Electrochemical Research Institute and was a visiting fellow at the Institute of Mathematical Sciences, Taramani, Chennai. Now, my area of research is the mathematical theory of high temperature superconductors. Now, I'm going to give a series of lectures on an emerging topic known as room temperature superconductivity. So, what is room temperature superconductivity? Or what is superconductivity, first of all? Superconductivity is the ability of some metals to conduct electricity without any resistance. So there will be zero resistance, and this phenomenon was discovered by a physicist Hendrik Kamerlingh Onnes in 1912, and the immediate year the Nobel Prize in Physics was awarded to him. He found that metals like mercury superconduct at very low temperatures, 4 Kelvin. They superconduct at 4 Kelvin. So that is what is known as the liquid helium temperature. And following Hendrik Kamerlingh Onnes' work, physicists were interested to shoot the TC. So what is TC? TC is the critical temperature, the temperature at which a metal, an ordinary metal, becomes a superconductor. So that is what is known as a TC. So in Kamerlingh Onnes' time, the TC was liquid helium temperature. Now physicists were interested to raise the TC, so that it can be the superconductor can be made available for practical purposes. So there were a lot of work going on, especially in alloys, but the TC could not be reached it could not be reached to a very high level. So from 4 Kelvin, they could go up to some, say, 12 or 15 Kelvin, nothing more than that. So then came the era of high temperature superconductors. So what Bednarz and Muller, they are the two physicists who gave birth to the so-called high temperature superconductivity. So what they did was they first analyzed what all compounds were studied for other than mercury and some metals which were showing superconducting properties. So other than that, what all elements were, or what all systems were showing superconductivity. So it was alloys. So in but in alloys, the critical temperature, that is the TC, could not be reached beyond 12 Kelvin or 15 Kelvin. So they thought that there's no use in pursuing any further alloys. But Bednarz initial work, or his area of specialization, was in single crystal growth of perovskite type oxides. So he explored the literature and found that some perovskite type of oxides were exhibiting superconducting properties. So what are all those perovskite type oxides? Strontium titanate. Strontium titanate is a perovskite type oxide that was showing a superconducting behavior, and then barium bismuth lead oxide. This was a type of oxide that was showing superconducting properties, and then lithium titanium oxide, Li2O4. This is a spinel type of oxide which was also known to exhibit superconducting properties. So what Bednarz and his boss, that is his mentor, Muller, did was they started exploring these oxides for their superconducting behavior. So strontium titanate was showing a TC well above around 2 Kelvin. Now this is though the TC is less than liquid helium temperature, still it was interesting that some metal oxides were showing superconducting properties, and that their TC can be increased by changing the properties of the oxides. So what Bednarz and his team did was they tried to increase the density of states of the superconductor of this metal oxide by doping it with niobium. So upon doping with niobium, they thought that they can increase the density of states. So increase the density of states. So this was one method by which the TC of the superconductor can be increased. Because according to BCS theory, the BCS theory is the Bardeen-Cooper-Schrieffer theory of superconductivity, which was discovered or invented some 50 years after Hendrik Kamerlingh-Onnes discovered the theory of superconductivity. The theory of superconductivity, as I said already, was discovered in 1912, and it was around 1950s, after some 50 years later, it was in 1957 that Bardeen-Cooper-Schrieffer theory was developed. So according to Bardeen-Cooper-Schrieffer theory, electrons, which are normally known to be charged like charged particles, are supposed to repel each other, but they can attract each other in a phonon medium. So that is what is called the BCS theory of superconductivity, and the glue for superconductivity is got from phonon exchange, a theory of quantum field theory. And what we are interested right now is in the TC. So what is the TC expression for in BCS theory? The TC is given by KB TC is equal to omega d e to the power 1 divided by the density of states at the Fermi level and the electron phonon coupling constant. So this is a rough idea. This gives a rough idea. It is not exactly the expression. It involves some other details also. But for the getting an idea of the variables or parameters that define the TC of the superconductor according to BCS theory, I have written this. So TC is given by omega d e to the power 1 divided by NEF into V, where NEF is the density of states and V is the electron phonon coupling constant. And omega d, H cross omega d, actually H cross omega d is the strength of the interaction between electrons when the interaction becomes attractive. So electron interaction can become attractive in a phonon medium. So they become attractive and form what is known as the Coulomb, what is known as a Cooper pair. So that strength of the interaction is given by H cross omega d, and this is the density of states, and this is the electron phonon coupling constant V. So what initially they thought was, just by increasing the density of states, the TC will increase. According to this equation, it is clear that when by increasing the density of states, the TC can also increase. So what they did was, so by doping some elements like niobium, they understood that the charge carriers can be increased in strontium titanate, and so the superconducting TC will go up. So from this equation, they tried to increase the density of states of strontium titanate, but this attempt failed. The maximum TC they can obtain was around, again, little less than 4 Kelvin. It didn't go beyond that. So that program failed. And so what they did was, they went to try other oxides. So the next oxide was lithium titanium oxide, Li2O4, but it had some chemistry complications. This is a multi-phased compound. Multi-phased compound means it is not phase pure. So a lot of phases will be involved, a lot of chemical phases will be involved, and so they didn't want to pursue this lithium titanium oxide. Rather, they tried to pursue this barium bismuth lead oxide. So by varying the elemental ratio, barium and bismuth and lead, by varying this ratio, they thought that they can vary the density of states and electron phonon coupling constant, and thus by playing with these two parameters in the BCS equation, that is by changing the ratio of the elements in this oxide, they can play with the parameters in the BCS equation, BCS theory. So by playing like this, they can change the TC. This was the Bednorz-Muller's initial idea. So they tried this, but this attempt also failed. And what they got was, they got metal to insulator transition. Initially it was a metal, it became an insulator. So it became a metal insulator transition, and the TC didn't go up. So that attempt also failed. Now the another thing they had to do was, the another oxide was also there, barium lanthanum copper oxide. So initially this type of oxides were used as catalysts in organic reactions, but this was also known to show some superconductivity. And what Bednarz thought was, they took some ideas from models such as the Chakravarti phase diagram and Hawk Polaron model. So according to that model, there some Jahn-Teller distortions should be taking place. So compounds which showed Jahn-Teller distortions were apt to produce superconducting transitions. So they thought that copper, because copper in this compound can show Jahn-Teller distortion, they thought that by playing with these parameters, the density of states and the coupling constant in this compound, barium lanthanum copper oxide compound, they can vary the TC and they can attain high temperature superconductivity. So similarly, so what they did was, they tried to vary the dopant ratios, and as they thought, they attained superconducting transition. So initially the TC was around 35 K. So there was a big jump from 4 Kelvin superconductor to 35 Kelvin superconductor. And this was what is known as this is why it is known as a high temperature superconductivity. So because within the trying to look from the superconductor perspective, 4 Kelvin is the normal superconducting transition temperature, but it has got shot from 4 Kelvin to 35 Kelvin. So that is why it is known as a high temperature superconductor. But I will explain later why all these things were not correct. They got this superconductor by some hook or crook, but in the physics of the problem was really wrong, because later two physicists, Macmillan and P.W. Anderson, they went on to look at Bednarz-Muller's lecture, and they said that as physicists, you cannot play with parameters at will. So these are the parameters. These are the parameters in the BCS theory that the superconducting experimentalists were playing about. But they were coupled in such a way that when one parameter is increased, the other parameter will decrease. You cannot say that just by increasing the density of states I can raise the TC, or by increasing the coupling constant I can raise the TC. When you are increasing the coupling constant, the density of states will go down, and vice versa. So the physics of this kind of physics was pointed out by these two physicists, and they said that, so the strategy by which Bednarz and Muller worked to get their superconductor was not correct. It was wrong. Though they got it by accident or by good luck, they got. But the physics of the logic and the physics was wrong. You cannot just vary parameters at your will. So that was the theory of that was pointed out by these two physicists. And so the theory of high temperature superconductivity was really challenging. You cannot explain high temperature superconductivity using the BCS type theory, which was based on electron phonon coupling. So electron phonon coupling cannot explain the high temperature superconductivity. So what was needed? So the initial solution to this problem was addressed by Professor P.W. Anderson, who brought about the so-called electronic theory of high temperature superconductivity. So where the degrees of freedom of phonons are not important, it is only about the electron interaction. So electron interaction in physics is known as strong correlation or weak correlation. So how the electrons interact with each other. So this physics of correlation was what was needed for understanding the theory of high temperature superconductivity. So this was the proposal of Professor P.W. Anderson, and I had actually worked with his student Professor Bhaskaran on this area. I'll be giving a series of lectures on room temperature on high temperature superconductivity, and how it helps to understand or gives guidelines to attain room temperature superconductivity. This will also be discussed by me in the subsequent series of lectures in February. So in February, in lectures in February, what I'll be discussing is, I'll be discussing what is meant by room temperature superconductivity, and some experimentalists have obtained some interesting results, but they are not reproducible. So what were those results? Initial results on room temperature superconductivity, or RTS in general. Room temperature superconductivity, or RTS in general. So some experimentalists have shown that. So what do you mean by room temperature superconductivity? It means that the TC will be at room temperature. You need not cool it at liquid helium or liquid nitrogen temperatures. You can obtain superconductivity at room temperatures. At normal temperature itself, the material will be superconducting. So that is what is known as room temperature superconductivity. Some physicists in the United States, Japan, and South Korea, especially South Korea, they have claimed to have obtained room temperature superconductivity in TC, but that is all not reproducible. So one time you do that experiment, you are observing superconductivity at room temperatures, and next time you do the same for the same sample, you are not able to obtain the superconductivity. So that is the problem. So it is elusive. Elusive means it is not certain. So you are not able to reproduce the phenomena. So I will discuss some of the experimental results, and the next thing will be, I will discuss about the prerequisites for understanding the electronic theory of superconductivity. So what are the prerequisites for the understanding the electronic theory? So you need to understand what is meant by the Heisenberg model. What is meant by the Heisenberg model of spins. So usually spin models are used to understand phase transitions. Spin models like Ising model, Potts model, and Heisenberg model. So we are going to use Heisenberg model to understand the theory of superconductivity. And so Heisenberg model, what is Ising model, what are their precursors? They are Ising model and Potts model are the precursors to the Heisenberg model. So a short understanding on what is meant by Ising model, what is meant by Potts model, and what is Heisenberg model, that will be given. And then what is meant by TJ model, TJ model Hamiltonian. So what is meant by TJ model? So these things I will be discussing in the next lecture. And the third one will be you can say resonating valence bond theory. Resonating valence bond theory of superconductivity. So what is that theory? That way I will be discussing. So to understand resonating valence bond theory, you should get an idea of what is meant by Heisenberg model, what is meant by TJ model, and then we will understand what is meant by resonating valence bond theory. So in chemistry, you all know that benzene has its own properties because of resonance. So the same resonance is happening here also, and it is able to explain some interesting physics. So this will be something like aromaticity in physics. So I'll be discussing this resonating valence bond theory and how it predicts that room temperature superconductivity is really possible. So experimentally, some experimentalists have obtained some results, but they are not reproducible. But RVB theory of superconductivity is saying that the results of RVB theory is saying that the TC can go even well above room temperatures. So what is the problem? Why it is irreproducible? It is irreproducible because the experimentalists are not able to control the experimental conditions. So that is why the results are failing. But theoretically, room temperature superconductivity is feasible. So that's what we want to. That's why we need to understand the theory of high temperature superconductors. And there are a lot of theories on high temperature superconductivity, but still none of them are satisfying. And RVB theory is a age-old theory, but still it can be modified. It can be given a new shape. So what will be that new shape? Already I discussed that resonating valence bond theory. You can see that the TC can go well above. It predicts that TC can go well above room temperature. The physics is all, though it is not wrong. I can't say, we won't say that it is sophisticated, but still it is logical, and it predicts that superconductivity can be observed even well above room temperature. So that's why RVB theory is interesting, but still it is not sophisticated. So how to make that theory sophisticated? So then next thing will be what is known as the variant Hubbard model. So what is the Hubbard? Hubbard model is the model of strong electron correlations. It's a model that is used to study strong electron correlations. Now, as we discussed earlier, in the high temperature superconductivity, the glue or the force which holds the electrons together, which causes an attractive force between the electrons, it is not because of the phonon media, but because of the electronic properties of the electronic properties. So electron correlation is that electronic property. How an electron interacts with another electron. So that is the that gives the glue, that gives an attractive force. It has nothing to do with lattice vibrations. So the theory of strong electron correlation is captured in what is known as the Hubbard model. So in that Hubbard model, there are two parameters, the T parameter and the U parameter. The T parameter is what is known as the hopping parameter, and U is what is called the electron repulsion, on-site electron repulsion parameter. So these are the two important parameters in the Hubbard model. And Dr. Bosco Emmanuel, from a retired scientist from Central Electrochemical Research Institute and also a visiting professor at the Institute of Mathematical Sciences, has modified the Hubbard model by saying that the critical part in the Hubbard model need not be U, but rather T. Usually it was U, but according to Bosco's model, that's why it is called the variant Hubbard model. It is not the U, but the T. The T by the correlation can be captured by studying the hopping parameter T. So that's why it is called a variant Hubbard model, and it explains really a lot of, it can explain really a lot of new physics. So this also I will be discussing variant Hubbard model of Professor Bosco Emmanuel. This also will be discussed by me in the series of lectures. But still, to understand the results of high temperature superconductivity experiments on room temperature superconductivity, to give a validity to that and to guide the experimentalists, merely resonating valence bond theory itself will be enough. But to go further and to make some sophisticated theory of high temperature superconductivity, one needs to work upon the variant Hubbard model. So all these things I'll be discussing in the series of talks that I'll be going to deliver in the month of February. So hope that you'll be delighted with my lecture series, and bye for all now. Thank you.